We'll discuss now metric, that is probabilistic properties of discrepancy for one-dimensional sequences. And to measure distributional properties, we consider first the local discrepancy with respect to a given subinterval of the unit interval. We just count here. This is the indicator function, the number of elements of the modulo 1 reduced sequence in the interval j up to some total number capital N, and compare with the Lebesgue measure. This is a difference, and then we count, then we discuss the extremal error. So we study all intervals j and take the supremum over the absolute value of these local discrepancy functions, or we just consider intervals anchored in the origin, which gives the so-called star discrepancy. So of course this is larger than this, but those quantities are more or less the same. They just differ by some possible constant, 2 in the one-dimensional case, and in higher dimensions, of course, it depends on the dimension, which is there more important. Another possibility for taking measures quantifying distribution properties is to take LP norms of the discrepancy functions of the local discrepancy. This gives the LP discrepancy. And in distribution theory, of course, it is known a sequence is equidistributed or uniformly distributed modulo 1 if the discrepancy functions tend to 0 for n to infinity if we consider an infinite sequence. And of course, it is interesting to know convergence properties of discrepancy functions. And the famous result of Wolfgang Schmidt says that such discrepancies cannot become arbitrarily small, and we always have a lower bound log n over n for infinite sequences. And in fact, this is optimal, since it is not very difficult to construct examples of infinite sequences with that discrepancy. One possibility is just to consider multiples of quadratic irrationals. Then we achieve that kind of discrepancies. You can take multiples of numbers with bounded continued fraction expansions. This is also possible for getting such low discrepancy sequences. But there are known a wide class of such sequences. Tomorrow in our workshop part, in the morning, in the online part, there will be some lectures concerning low discrepancy sequences which can be easily constructed, like van der Corput sequences and higher dimensional versions of that. Okay, as I mentioned, I am more interested in probabilistic aspects, and this was originally in the focus of Hermann Weyl in his seminal paper in 1916, where he introduced equidistribution as a general concept. And he proved, in fact, that a sequence an times x, where x is a real number and an is a sequence of integers, is equidistributed for almost all x. So a typical sequence produced by multiples of a given sequence of integer is equidistributed. And lambda, as I mentioned, is the standard Lebesgue measure. So this was a result at a very early time. And of course, it became an interesting problem to study the discrepancy of such sequences. And this was done step by step. I do not mention all work in this direction, but the classical approach is due to Erdős, Gall, and Koxma in the 50s, who developed a very beautiful machinery concerning exponential sums and estimates of moments of exponential sums. They only considered variances and achieved this discrepancy bound here, written in green. So for almost all x, one could get a bound power of a logarithm over square root of n. Square root is very typical for metrical results here in the denominator. You know a random sequence behaves more or less from the point of view of discrepancy 1 over square root of n, a purely random sequence. And this is a probabilistic result which we should have in mind. We want to imitate random behavior by some deterministic approach to the construction of the sequences. So this is quite natural. The interesting fact, of course, is what we can say on a more finer estimation of the discrepancy. And this was the first result. You see the exponent here is 5/2 plus epsilon, and it took quite a while to improve this exponent significantly, and this is due to Roger Baker in the 80s. He could improve the 5/2 to 3/2. But it seems a small improvement, but nevertheless, it was necessary to apply the Hunt-Carlson theory from Fourier analysis, which is a deep machinery which was not available in the 50s because Carlson achieved his famous result on pointwise convergence of Fourier series in the 60s. So, and using this machinery, Roger Baker could achieve this very, very beautiful result. And I will go further on in the discussion by assuming additional properties on this sequence A(n), which I sometimes also denote by nk. So this is a subsequence of the integers always. And I try to get better results than log to the 3/2. And in fact, I will approach sharp results, which are optimal what is concerned to the power of the logarithm. And in classical Fourier analysis, such sequences having stronger analytic properties were already discussed in various aspects, and they are called Lucunary sequences. A Lucunary sequence, simply spoken, is just an exponentially growing sequence. So this is Lucunarity with growth rate bigger than q, which is bigger than 1. A subsequent, increasing subsequence of the integers. And in the classical days of Fourier analysis, Salem and Sigmund already obtained a central limit theorem, so CLT stands for central limit theorem, for summation, for trigonometric sums over Lucunary sequences. So you see, this is a cosine sum for simplicity. This is correctly normalized. And as a distribution, we get standard normal distribution here. And similarly, a little later, Erdős and Gall, I already mentioned, for their discrepancy results, obtained a law of the iterated logarithm. So for that trigonometric sums, this is the correct normalization here. And you see, so to speak, trigonometric sums over Lucunary sequences behave like random sequences, because law of the iterated logarithm and central limit theorem are well known from probability theory of sums of IID random variables. So trigonometric sums, although this is not, does not have independence here. These are not independent expressions, because there is, if you compute the corresponding integrals, there is some overlap, but they behave like random sequences because of the nice analytic structure behind, clearly. So, yeah, what is the aim here? We have three aims in the lecture: extensions to more general functions, not only consider trigonometric ones, considering discrepancies instead of functional evaluations, and of course we want to switch to more general sequences than Lucunary, so we would consider sequences of stronger growth and of weaker growth and show how randomly do they behave. So we want to analyze the distributional properties of that kind of sequences comparing with true random sequences. What are the differences and what can be observed? So let's start with the program. I should say this is a big project. I was interested in that questions, say, more than 15 years. And it is a program jointly with Christoph Eisleitner, who is now in our department, a professor in our department, a former PhD student of István Berkes, who now is retired and lives in Hungary, and myself. And for instance, we could achieve a result for arbitrary functions, f instead of the cosine functions. You see the power of the log is 1/2, which is better than 3/2 of Roger Baker. But of course, we are assuming Lucunary. Roger Baker didn't assume anything on the sequence, just increasing integers. And we get some further correction term, which is a double log almost everywhere for x. And we know optimality except the value of this exponent here. So log to 1/2 is optimal. And this we are happy, of course, because the double log, so it's our numerical analyst colleagues say a double log is a constant. Yes, so a double log is a constant. Okay, number theorists, of course, believe that. Don't believe in that, but okay. And we have, you see, we also have lower bounds, 1/2 here in the double log, so there is a little gap in the double log. Okay. And we are also able to extend that for more general sums with weights ck here if we assume a convergence property on the weights. You see, people interested in Fourier analysis know something behind that. L2 convergence on the weight in general is not sufficient. L2 convergence on the weights is sufficient for trigonometric summations. And this is exact Carlson's theorem I mentioned before. In general, orthogonal series theory, you have to use here further weight functions to ensure convergence, and this is done here too, yes? Okay, so what we also were interested in, as I mentioned before, is laws of the iterated logarithms. So not only central limit laws, laws of the iterated logarithms, and the starting point was my joint work with Walter Philipp, and of course the original starting point was Walter Philipp's own work. He was able to prove an Erdős conjecture. Paul Erdős asked this conjecture in the 60s, early 60s, and Walter Philipp gave a proof in 1975 in the Acta Arithmetica paper. And the question was, does the discrepancy function satisfy a law of the iterated logarithm for Lucunary sequences? And Walter's result is this law of the iterated logarithm, correct normalization here, which is the standard normalization from probability theory, and this is bounded, this lim sub, with a lower bound given very explicitly, and with an upper bound depending on the growth factor q, which can also be given explicitly. I will discuss it later, holding, of course, for almost everywhere for almost all x. And of course, the next question, which we discussed in our project for years, is to compute this lim sup. And of course, it's not clear that this lim sup is a constant. It could be dependent on x. It could be a function of x, clearly. And this is a very interesting question I will discuss soon. For instance, in some cases, they could be treated very successfully if nk is just a power of a number, which is bigger than 1. Of course, this is an exponentially growing sequence, and it could be, of course, an integer, but we also allow that this number theta is some number bigger than 1. It's also a Lucunary sequence in a wider sense. And it turns out the most easy case is the case when the growth rate is super exponentially. Namely, the lim of the quotients is infinity. This is, of course, a Lucunary sequence, but I call that super Lucunarity if the limit is infinite. And then it's easy to compute this lim sup. It's 1/2. Easy. It's possible. And people coming from probability, of course, realize immediately this is the correct value for truly random sequences. It's, Chung-Smirnov law or whatever you call that. It's the law of the iterated logarithm for sums of independent random variables. So for super Lucunary sequences, we get truly random behavior in that sense. For the Lucunarity standard one, it becomes very delicate, and I should mention the final solution of computing this constant is due to our Japanese colleague Fukuyama from Kobe University. He could compute that completely, and you see it is also quite easy if this here is irrational. If theta is, the complicated case is if theta to the r is irrational, yes, for some r. It turns out the value of r is not important, but important is that the power of theta is an irrational. If theta, for instance, is transcendent, then this cannot happen, and then the behavior is like in the case of super Lucunarity. 1/2, yes? But the difficult case is this one. And let me explain it a little bit. I just discussed the case when theta is bigger than 1. It could also be done if theta is less than -1. Yeah, because then it's also maybe sign change, but in the absolute value it's growing. This I don't consider here. And you see here a complete list of cases. P and Q odd. This value of the constant sigma theta is this value. P bigger than 4, even. Q1, this value. P2, Q1, strange value, square root of 45/9. And in the case that one of the P and Q is even and the other is odd, similar but more complicated formula. Just to explain this example, you see huge quadratic irrationals show up here in the computation of these constants. So there is a delicate arithmetic behavior. As I mentioned before, if theta is transcendent, the outcome is 1/2. This is due to Fukuyama. So you see the behavior is almost random. We have a law of the iterated logarithm, but not totally random. The constant could be different. Strange values of constants show up here. Okay. Now, of course, it's also interesting not only to consider theta powers, but maybe subsequences of powers, or even permutation of elements. Clearly, if you have true random sequences and you permute the elements of the random sequence, you again get random behavior. Yeah, so pi k is just a a bijection of the positive integers, a permutation of the natural numbers. And random behavior is independent of permutations. However, here we observe a difference, and I will explain it to you. The corresponding constants, these values, sigma, now of course depend on these subsequences nk, or respectively on the permutations. They lie now in the interval, you see, left hand side 1/2, which is the value of the constant for the true random sequences or for super exponentially growing, and some constant sigma theta k, where this is the constant we just computed above for I did something wrong. The constant we computed above for powers of theta to the k. So the subsequence nk is k, so we have theta to the k. These are these constants we already computed here. And you see here, furthermore, this work, which is mainly due to Christoph Eistleitner, showed that the value of CQ, this upper bound in Philip's result I mentioned before, can be made explicitly and very nicely what is concerned to the dependence on Q. It turns out that for big Q, have in mind Q is the growth rate of the sequence. It is 1/2 plus capital O of 1/Q, where we were very careful, where the constant of the 1/Q can be made explicit, and then there remains an expression which tends to 0 more fast than 1/Q. But the essence of that is, asymptotically, we get 1/2 for the constant if the growth rate tends to infinity. So this means that Lucunary sequences with exponential growth, Q and Q going to infinity, behave like true random sequences. So we have optimal behavior here. And if you remember, I mentioned before that in the law of the iterated logarithm here, in this Philip's law of iterated logarithm, we not necessarily get a constant here. It could be dependent on x, and this becomes clear if we analyze the permutation invariance of the results. So we don't take just a sequence, theta to the k, but we allow to permute elements of the sequence. And strange things occur. For instance, if we take as a subsequence nk, which is this very strange sequence, or if we just take as a subsequence nk powers of k minus 1, so you would suspect this doesn't make any difference if we take theta to the k or theta to the k minus 1. And already Erdős, with a co-author Forte, found that this makes a big difference. It, so to say, not only growth rate is important, but also the arithmetic structure of the sequence, the subsequence taken out, is of importance. And you will see that soon. So, for instance, the Erdős-Forte observation was concerned to summation, not to discrepancy, normalized summation. And it turns out that this has non-Gaussian limit theorem, so not anymore Gaussian, and that the lim sub is not constant. So you see this phenomena already in this early stage example. However, for the discrepancy, the Erdős-Forte sequence gives a constant lim sub. It's just the same as for the original sequence. So here you don't see the difference of this little arithmetic change. However, if you move to the star discrepancy, remember the star discrepancy was the discrepancy only with respect to intervals anchored in the 0 point. So fixed 0 to x and taking the supremum. And if you take this little variant of the problem, then you can find that in countably many cases, for instance, in the cases theta being an integer, positive integer bigger than 2, p in my notation from above, the value of the sigma, so this lim sup, star means with respect to the star discrepancy, now is not a constant. It's a strange function which can be computed explicitly, but it's not a constant function. And as I mentioned already before, for transcendental theta, you always get the, so to say, correct value, the value as it is known from classical probability theory, 1/2. And for this strange example here, you already get a non-constant value of the sigma, even in the case of the usual discrepancy, not of the star discrepancy. This is the reason why I mentioned also this example. You can find examples for counterexamples for ordinary discrepancy, but they are more complicated than for the star discrepancy. Here, this nice example is enough. Okay, so let us now move from the so-called Hadamard gap condition, which is lacunarity. This is also another word. Exponential growth, Hadamard gap condition, lacunarity means always the same. Exponential growth of the sequence. Different names for the same property. And here, it's useful to introduce this growth quantity. So we count how often these elements nk are contained in dyadic intervals, and we take the L2 norm of these properties here, so the quadratic means. And if we know upper bounds for these quantities, you see this bound here, for some technical exponent alpha, and uniformly in R, which is the size of these dyadic intervals, then we get a law of the iterated logarithm again with some constant. So it's possible to extend Philip's result to these more general classes of sequences with technical conditions. And I will discuss these conditions in the following. And here it turns out what I already have mentioned. And this is why I like this topic very much. It glues together a philosophy from harmonic analysis. So the tools we use here are classical harmonic analysis and modern aspects of probability. So for estimating, for computing these constants, you have to estimate norms. So you have to estimate moments, variances, even higher moments, 4th moments, 6 moments. And for estimating these moments, we use martingale inequalities. Standard inequalities from probability. You see dyadic chaining and that kind of analytic arguments. But this is not enough. One has to use the arithmetic structure of the sequences behind, and you will see which kind of arithmetic properties we will use. We will use estimates for the number of solutions of Diophantine equations. So, and this is what I like, because I feel myself more an analyst than a number theorist. But of course, I do number theory, and this is a point where modern number theory, Diophantine number theory, glues together with analysis in a very deep way. And yes, so what kind of Diophantine equations we use here? We use, of course, in order to estimate moments of exponential sums, we get, for the second moment, for instance, in the exponents, expressions of this shape. A times nk minus b times nl, and we have to look whether these exponential sums become big or small. Integrals over exponential sums. When is an integral over in an exponential function small? If the exponent is not zero, it is not zero, because then it's 1 and adding up this is big. If the exponent is some function k times x, where k is not 0, then of course it's periodic and the integral vanishes. So for us, bad expressions are when these sums or differences become 0 or another constant which can be extracted, so the remaining part is constant. And so we have to count the number of solutions of that kind of Diophantine equations. And my property D, remark D, Diophantine remark, means that the number of solutions can be estimated in terms of the total number n with an exponent which is not bigger than 1. For fixed coefficients and important, uniformly in C, which is not 0, the case 0 is an extra one. And if we know this property, we again get the correct value of this constant sigma of this lim sup, which is again 1/2 known from probability theory. As I mentioned before, we were also interested in comparing permutational results with the permutational results of classical probability theory, and assuming again Adhamar's gap condition, so exponential growth, sigma be a permutation of the positive integers, we observe the correct theorems. So that means, of course, a theorem is always correct, but it's meant in a meta language. So correct in the sense like in probability theory. Central limit theorem with standard normal distribution, not standard, 1/2 is the variance here, as I mentioned before, centralized here, and similar for the lim sup, so for the law of the iterated logarithm, correct normalization here. And of course, distributional convergence here and usual probability space I just mentioned. It should be also mentioned, and this is a quite old result of Walter Philipp and Istvan Berkes. They showed that central limit theorem and law of the iterated logarithm remain valid under weaker growth assumption. This is the so-called Erdős-Takahashi condition. You see the quotient now can approach 1, but not too fast. The quotient, it's not necessarily exponentially growing. It can approach 1, but not too fast. And if we have that, the unpermuted central limit theorem and law of the iterated logarithm remain true, provided that alpha is not too big, so less than 1/2. And they were able to construct a counterexample if alpha is 1/2. Yes, so you see, it's a very fine classification of these probabilistic limit laws. Even finer than lacunarity or non-lacunarity. It gives an exact answer, but only in the non-permuted case. In the permuted case, you will see the situation is different. Yeah, as I already mentioned, in the super exponential case, it's easy. We have a very general law for summation of functions. It's enough to have a one-periodic centralized function which is of bounded variation, so a quite nice regularity condition, nothing else has to be known. Then we have permuted for any permutation central limit theorem with the correct quantity. Here it's just the variance of the function f, and just here the standard deviation of the function f for the law of the iterated logarithm. So Beautiful behavior. And under the Hadamard gap condition, you see it here is super exponential growth. If you reduce it just to standard exponential growth, we need more to ensure permutation invariance. And what do we need more? We need remark D. That means assuming that Diophantine condition, counting the solutions of the Diophantine equations, replaces exactly the superlacunarity. And having in mind my discussion earlier on the Erdős-Forte counter example, we have seen that theta to the k and theta to the k minus 1 give different results. Permutation invariant, not permutation invariant. And of course, theta to the k minus 1, if you compute the number of solutions of the Diophantine equation, you will see that there you have too many solutions of the Diophantine equation. And this is the reason why the result becomes false in this case. If you have this condition, you again get correct limit laws here, and the constants are clear. This is the gamma constant. Gamma is this constant here in the general case. And here you get gamma, square root of gamma is the constant here, and gamma is the constant here, and gamma in the general case is this value. And you see, this depends, of course, on the permutation sigma if you compute these variances here. Now, the next step. We want to understand if it is possible to get rid of all growth conditions. The answer is yes, that's possible, but then you have to screw on the Diophantine conditions. If you have no information of the growth, no analytic information, you can compensate that by assuming more arithmetic information. And here we have to achieve more general Diophantine equations. You see, this is a Diophantine equation of the length p. P is non-zero, constant, and we need the information that the number of the non-degenerate solutions of that equation is at most some constant Cp. What means non-degenerate? As in Diophantine number theory, non-degenerate means that no subsum of the whole sum of lengths p vanishes. This is a non-degenerate solution. No subsum vanishes. Yes, like in Schmidt's theorem, or Schlickeweiss theorem, or whatever, on this subspace theory, non-vanishing solutions. Yeah, and if we assume nk to be a sequence of increasing positive integers having this property AP, for all p bigger or equal to 2, sigma a permutation, gamma this value of variances just defined before, then a permuted central limit theorem is always true. And if we know a little bit more on the Diophantine condition, then we also know a law of the iterated logarithm. And a little bit more is an upper bound for the constants. And the upper bound is just an exponential of p to the alpha with some alpha, which is double exponential, but not triple exponential. You know from Diophantine number theory, the bounds can be increased very rapidly, and it depends how fast they are growing. And this gives then possibilities for computing solutions and so on and so forth. Okay, this is what we need for that. And now we have a very, very beautiful example. It's a classical example going back to Hardy, Littlewood, Polya, to the early days of Fourier theory and analytic number theory. It's the so-called Hardy-Littlewood-Polya sequence, and it was also very nicely used by Hillel Fürstenberg in his famous work on dynamical systems in the 60s, proving density of orbits of dynamical systems. And the sequence is the following. Take the multiplicatively generated semigroup of a finite set of co-prime integers. So for instance, take one integer, 2. The multiplicatively generated sequence is, of course, by one generator are the powers of 2. Yeah, good, this we know. This is theta to the k, and this is a Lucunary sequence, so we know everything from what I have mentioned before. But if you have 2 generators, 2 and 3, you take the multiples, 2 to the k, 3 to the l, you order them in increasing order, you get an infinite sequence. This is not anymore Lucunary. You can, it's an easy exercise for calculus students in the first year. You can ask them to find growth bounds, and you will see it's not Lucunary. It's a little bit less growing than exponentially. And if you have more generators, it is not Lucunary. Only in the trivial case, it's case 1 generates Lucunary. And Fürstenberg, as I mentioned, proved the densities by a dynamic approach. Rob Tiedemann in the 70s, using Baker's linear forms in logs, proved the lower bound. And this shows, of course, that it is almost exponentially growing. Then you see there you have in the denominator log nk to the alpha. If this is cancelled, so if alpha is 0, then of course it's exponentially growing. And so this is exponential growth is only disturbed by a logarithmic factor. And a quite recent result is a result of Amoroso and Viada in 2009, a very, very nice, beautiful application of a strong version of Schmidt's subspace theorem. It's the version of Schmidt, Schlickewey, and Evertse in the Annals some years earlier. And with that machinery, one can achieve an upper bound for the constant in my AP property I mentioned before in the for the number of solutions of a Diophantine equation of length p. And you see x to the p to the 6. Remember there the requirement was x p to some alpha. Alpha is 6 here. Of course, it's a nice question to improve and so on. You can think about, but it's not necessary for my application. Using what I have mentioned before, we get for this sub-exponentially growing sequence central limit theorem, and we get even law of the iterated logarithm with permutation invariance, because everything is satisfied. So we have a sequence slowly growing and definitely having these properties. The reason is clear. The arithmetics is beautiful. Yes, so we compensate analytic mass by arithmetics. I should mention an old result of Kit Nair, who found a very strange general result for these Hardy-Littlewood Polya sequences. And he was able to consider functional sums over one periodic functions where the function is only required to be measurable. You see, equidistribution theory always needs continuity of the functional evaluation, or at least Riemann integrability. So, or as I mentioned, total variation is bounded. To get useful estimates for discrepancies, you need that. Of course, you can ask whether a limit theorem holds for measurable functions, and usually that's not true. There is this famous counterexample of Mastrand and so on. So this is not, but if you insert such sequences coming from the Hardy-Littlewood Polya sequence NK, we get this limit relation, which usually gives uniform distribution for arbitrary measurable one-periodic functions. And Kit Nair calls that strong uniform distribution. This is a very rare property. You see also here, arithmetic replaces analytic deficits. Yes, so that's a philosophy here behind. Okay, and now I'm approaching the end of the talk, and you have seen the philosophy was to glue arithmetics and analysis to analyze discrepancy in a metric sense for such sequences. And I tried to apply various techniques from Diophantine number theory, but the philosophy was a non-algorithmic philosophy. So to get understanding of random properties, how far are these deterministic sequences away from being truly random? This was a philosophy I was also interested in many years ago, and the reason for that was a more algorithmic reason. If you look into Donald Knuth's book, The Art of Computer Programming, second part, there is a very beautiful chapter on random numbers. How to test random sequences by deterministic test, what means random for a given sequence. For instance, normality is a concept. If it behaves normal, it satisfies in some sense a random behavior of a sequence, yeah? Because all blocks occur with the correct frequency, as Manfred mentioned before, and so on and so forth. So this is one concept. And Donald Knuth discussed various other tests or concepts. For instance, you can ask, is a sequence produced by a linear recurring scheme? Behaves that randomly? Now, of course, not in a true sense, because a linear recurring scheme produces a periodic sequence. That's not random. But if the period length is long, very long, it behaves almost random in some sense. And in fact, such sequences are used on any computer for producing random numbers. Yes, the random generator is usually based on a linear recursion with high periodicity. And so Knuth formulated a lot of conditions, and the strongest condition he formulated is the following. I call it super pseudo-randomness. Yeah? Pseudo-random means a criteria, deterministic property comparing a sequence with random sequences. For instance, I could also postulate a new criterion, taking a law of the iterated logarithm with constant 1/2. This is my criterion for randomness. Of course, for possible applications, it may be a weak criterion. For other applications, it may be a good criterion. It depends what criterion you take, depends on the sort of application you want to use. For instance, discrepancy is always a good criterion for numerical integration. But if you want to apply your random numbers for simulation of stochastic processes, it may be not a good criterion, because a sequence with low discrepancy can be very regular in some way. And then for a stochastic process, it's not so good. So it depends. And so this was the reason for Donald Knuth discussing several concepts, and the strongest one he had is this super pseudo-randomness. And here is the formulation. For any computable subsequence, so the NK are again my subsequences of the positive integers. What does computable mean? Yeah, and you have an algorithm to produce the subsequence. For instance, if you be a rigorous person, take a Turing machine which selects the subsequence. Yeah? This is a computable subsequence. So you cannot take a generic subsequence, because if you take almost all selections of the positive integers, they are not computable, clearly. Yeah? So computable means there are only countably many of them. Yes, otherwise it's not formulatable. It's not possible to formulate it with a Turing machine. Yeah, so for any computable subsequence of n, take the S-dimensional sequence. This is the first and last point where I consider multidimensional aspects. I mentioned at the beginning, I will do it only at the end. So S-dimensional, this means you take blocks, as Manfred did, and the blocks consist of x and k along this subsequence. The second coordinate is x and k plus 1. So the second, I shift the subsequence one step further, and I do that s steps. So the s component is x and k plus s minus 1. So if I count these blocks, as Manfred did, I check normality in some sense. So I check normality here, and I am, of course, my sequences are real numbers. The xn are real numbers. So Manfred only checked digital sequences. So the alphabet was 0 to b minus 1. Here my alphabet is the unit interval, so unit interval. And these blocks should be uniformly distributed mod 1 as S-dimensional blocks. So what I do is I study points in the S-dimensional unit cube, and I'm looking whether they are uniformly distributed or not. If you want to have a rigorous definition, you can just formulate it by Weil's criterion. You have exponential sums, and in the exponents you don't have multiples of one coordinate, integral multiples, but you have here all coordinates in a linear combination, where the linear combination is not allowed to be trivial. So the factors are not 0, not all factors are 0, and this mean has to converge to 0. This is one possibility to formulate equidistribution of sequences, and if this is a points in S dimension, this is the correct S-dimensional formulation of equidistribution. And the conjecture of Donald Knuth was that the sequence x to the n powers are super pseudo-random for almost all x bigger than 1. This was open for several years, and in a joint work, my first joint work with Harald Niederreiter, we could establish that conjecture, give a proof, and later I gave a quantification of the proof some few years later, and this was the final solution of that problem. And many years later, Christoph Eistleitner got interested in that problem, and he was able to achieve a law of the iterated logarithm in the style I mentioned before for that kind of sequences. However, here are open problems behind. For instance, the constants, the values of the constants are not known up to now. The calculations become here very involved. And what is also not known and I excluded it completely in my talk, are multidimensional variants of the problems. So the field is quite open, and I should conclude here. So if my period here in Marseille is over, I try to produce a volume as some of my predecessors on the Morley chair did. Some volume, they did it with Springer company. Maybe I do it with another company. It depends on my discussions now in some minutes at lunch. And this will be a main point of this volume. I will connect arithmetics and analysis, and I will see if some further new results can be worked out in this program. I should also advertise this volume. I hope that it will be produced. So it's an advertising on an unsafe project. We will also include work on Sarnak's conjecture beyond that, what is already found in the Morley volume of the project of Mariusz Lemancik. There is a big article, survey article, and we Joel, Michael Dermota, and Clemens Müller, who had very nice results in the Duke Journal on Sarnak's conjecture for automatic sequences. This will also be a part of this volume. So it will be some glue of randomness, determinism, some applications, which was the idea of this Morlaix semester, and I hope some of you will read this volume if it will exist. Yes, okay. So thank you very much. And if there are questions, so for the people here in the audience, we can do it during lunch or in the discussion session, which is at 3:15 in the afternoon. Okay.